Welcome to another podcast. This episode we're going to take a look at the method of reflections. This is the way to adjust D'Alembert solution when there are boundaries involved. And so the main question that we're trying to answer here is what happens to characteristics at a boundary? And the main way that I want to preface this is just imagine, so this is the case that we're going to be in. Imagine that you're holding a rope, you're tethered at this one spot, so this is a fixed boundary, which if you remember is the Dirichlet boundary problem. So we're essentially looking at the wave equation for this example, where we're only defined for positive values. The boundary condition is u of 0 t equals 0, so this is the fixed left endpoint, the Dirichlet condition. And the initial, let's say the initial wave is f of x, and the initial velocity at each point in the wave is given by g of x. Then, based on what we understand about characteristics, which admittedly is maybe not a ton at this point, but we're getting better. Based on what we understand about characteristics, this is what we have to consider. Our characteristics are of the form x minus ct, so let's look at the sort of the edge case here. And that is this line. This is the line x minus ct equals 0. And basically that characteristic divides the region. So this is space-time, so it's x versus t. Divides the region into two zones. I'll call this region 1 and region 2. Region 1 has the property that x minus ct over here is, that x is greater than ct. And region 2 has the property that x is less than ct. So we're either ahead of the wavefront or behind it is basically how you would view it. And so I want to consider what happens in region 1 to start because it's the easier case, and then we'll go to region 2 after that. So region 1, any point in region 1, if you backtrack the characteristics, so I need to make it parallel to this blue line, so backtrack, and then we need a perpendicular, something like that. Remember, the definitions in the book for these terms is this interval is called the domain of dependence, and the region here is called the region of influence. Well, it's not quite the region of influence because from a point, we'll call it the domain. This region is the domain of dependence. The region of influence is something a little bit different. We'll talk about that if we get a chance. But the point is that entire region stays in the region 1, if you will. And in region 1, both of these initial points, so the 2 points that are being mapped here, the points, we'll just call them x0 and x1, both of those points have the property that they lie entirely within the region where x is greater than ct. Because here's what we need. In region 1, so in region 1, the solution for all points in region 1 is given by D'Alembert's. Because if you look, let me just go ahead and write down D'Alembert's solution. And, in particular, if this is the point x0, then this is the line. So let me change my notation a little bit here. Let me call this the point x0, t0. Then this will be the point x0 minus ct0. And this will be the point x0 plus ct0. And what I want you to see here is both of those values are positive. So if I plug x naught and t naught into this solution, then I get positive values for f, positive values for g. And the reason that that's important is if you back up to f and g, they are only going to be defined for values of x between 0 and infinity. So nothing goes wrong as long as you're in region 1 is basically the idea. So the question now is, okay, well, what happens if we are in region 2? What should we use as our solution? Now, in order to demonstrate this, I'm actually going to draw a different figure. So I'm just going to go directly below it here. And we'll do the graph for region 2. So once again, let's draw in the sort of the dividing characteristic, if you will. And let's consider the point in region 2 given by, once again, x naught and t naught. All right, if I draw the characteristics in, so I'll do the characteristic here in, let's say, let's just do yellow. So I need to make it parallel to the blue and perpendicular to the blue. So I'm running out of zone here. Just enough. All right. So let me extend this over a little bit. Okay, if you take a look at this, then at this point right here and this point right here, those are the regions which are, or those are the initial values that contribute to the solution at x naught t naught. If you look at the previous video, we talked about characteristics. These two initial points along the wave and everything in between tell us what we need to know about the point x naught t naught. But here's the problem. I don't know, this is undefined. I don't know what the value of f or g is there, and I don't know the value of g or f anywhere on that interval. So the question that we have to ask ourselves here is, what can we replace f with? What can we replace f of x and g of x with to give us information about these points? It turns out that the remedy that we use is in this case the odd extensions of the functions f and g. Now we talked about odd extensions in class the other day. Remember that the odd extension of f is just the basically you look at the symmetry of f. So, well, let's just go ahead and define it. The odd extension of f is defined as the function f as long as you stay greater than 0. It's the function minus f of minus x when x is less than 0. And because it's the odd extension, you have to give it the value 0 when x is equal to 0. You just have to make sure that that's the case. So if we use the odd extension instead, then this value over here is no longer undefined. It's just going to be the value of the odd extension at the point. So this point here would be x naught minus ct naught. But look at how we've defined that. F of x naught minus ct naught is equivalent to negative f of, so look at how it's defined since we're less than 0. Since x naught minus ct naught is less than 0, the odd extension is defined as negative of the original function we actually know something about minus x. So reverse this, it should be c t naught minus x naught. And here's the point, we know all about this function. We can actually calculate that value. So that's going to give us the value of f at the point x naught minus ct naught in terms of its odd extension. And graphically, there's something really incredible going on here. basically the idea is when this characteristic hits the boundary, it reflects, and this is why this is called the method of reflections, it reflects along a characteristic line. If you know the law of reflections from physics, you know that if it comes in, it's going to reflect perpendicular in this case. So this red line is a characteristic line itself, and what we know here is this point over here was x naught plus ct naught. That point was fine because it's greater than 0. I can just use the value of f at that point. Here, we had to use the reflected value of f, and the reflected value of f is the value at ct naught minus x naught. So that ends up being the exact point that we needed, c of t naught minus x naught. And so the region that's impacted here is we no longer need to consider what happens in between x naught minus ct naught all the way up to x naught plus ct naught. Instead, what we can do is our new domain of dependence is in between these two new points. That's all the solution depends on. And the values in here are basically the propagation, in other words, along here is inside this parallelogram. So this is a parallelogram that forms the region of influence for these two particular points. And so you can see that every single point above this line x minus ct equal to 0 is going to bounce off the boundary or rebound off the boundary. So in particular, when you have a point in the region 2, what you do is you slightly adjust D'Alembert's solution to be, in this case it's f of x plus ct minus f of, so it's the odd extension, right? This is the point where we have the problem. It becomes minus f of ct minus x plus 1 over 2c. X minus ct becomes ct minus x to x plus ct, because remember it's this region now, g of s ds. So if you look in your book's going to have two different formulas. It's going to have one formula if you're ahead of the waveform, and it's going to have a different formula if you are behind the waveform. And what I mean by the waveform is this sort of leading edge from the boundary. And so those are the two formulas that you obtain, but I want you to understand the method here because we don't want to write down a bunch of formulas for a bunch of cases. We just want to understand how characteristics interact with the boundary. And in this case, we needed to use the even extension in order to accomplish this. Now, we're going to talk about in class why the even extension, but here's sort of the question that I want to leave you with. If we have a different boundary condition, so if the boundary condition changes, and remember the boundary condition here was the Dirichlet condition, so if the boundary condition changes, does the formula for u of xt change? In particular, what do we use? Do we still use the odd extension, or do we use a different kind of extension? And that's a question that we're going to talk about coming up. It's also a question in your book, so think about the Neumann condition. If you had a Neumann condition there, so you held the end of the string at a constant slope, how would that affect the solution in this case? All right, thank you for watching.